Hello and very welcome to this video where I'm going to give you the basics for understanding data types in the new RealFlow graphs. Okay, before getting into the matter, please let me explain for those of you that don't have programming skills what a variable is. It's a very simple concept. Variable is a portion of the computer's memory where you store something so your computers can remember it later on. For instance, imagine that you want to multiply two different numbers. What you are going to do is just to put those numbers in your computer's main memory. In this case, I'm going to multiply the number 3 and 4. And after that, your computer's processor will get those numbers from the main memory and will perform the multiplication in this case. Okay, now how this look like when you are using a programming language like C in this particular case. Here you see that we have three different variables, A, B, and C, and please notice the tag, the word int before the name of the variable. Int stands for integer, and in this particular case my variables are of type integer. This case is a good type for doing the operation that I want to do. It is very important for the computer to know what type is the data you want to store in memory, since it is not going to occupy the same amount of memory to store a short number than a large number, for instance. The type is also very helpful for the computer to interpret the data stored in the variables. Before going on with types, please let me bring a node to a graph. So for that, let me swap the single view panel to the patch graph panel so I can create nodes in here. So I'm going to create a node which is of particular interest for showing you this. So this is the image ocean statistical spectra. This node, as you can see, has a lot of inputs, and you can see that the different input pins here have different colors. The color is related to the type of that pin. So if I right click on the pin, context menu will be shown, and you can see here how this particular pin is of real type. Forget for the moment about the number inside the brackets. So now if I bring a constant real node that basically is a real variable, you see that the colors are pretty much similar. So if I try to connect this output pin to some of the input pins in the ocean statistical spectra node, you will see that the nodes that are not compatible with this type are grayed out. So, for instance, scale input pin, if I right click to find out its type, you will see that we have here the vector 3 type, so it's not compatible. So if I bring a constant vector 3 node, it will create a vector 3. So in this case, only the scale input pin is going to be available for connection. So when I realize the connection, when I create actually the connection, you will see that the line connecting the two different pins is having the same color, that the type of the pins. In RealFlow graphs, we have the following basic types. Bit, and this type can be used to represent variables that can have only two different values, two different states. Normally, you can think on true and false or 0 and 1. For those of you with programming skills, I want to stress out the idea that when you are using arrays of this type, internally we are using just 1 bit for internal storage. So array of bits are quite efficient in terms of memory consumption. Next type, integer, can be used to represent integer numbers. You know that an integer number is a number that can be represented without a fractional or decimal component. For instance, numbers 1970 minus 3211, the number 4, etc. As you can see here, the range for integer numbers is from minus 2 billion to 2 billion approximately. So a lot of different, quite wide range of numbers can be represented using the integer type. The next type, integer 64, can be used to represent large integer numbers. You can see here the range is crazy, is approximately from minus 9 quintillions to 9 quintillions. This is an example of a number that can be represented using this type. So now, why do we need to represent such a huge number inside RealFlow graphs? Well, the reason is mainly because of the ID of the particles. I mean, it doesn't mean that we are going to have that amount of particles in our scenes. But you know that the particles ID in RealFlow are not reused. So if you are creating and removing particles continuously, especially within hybrid or two secondary emitters, like for instance plus is created and destroyed when it hits the surface of the fluid. So in that process, you might run out of valid ID numbers for particles. So for that reason, particles ID in RealFlow are represented using this data type. The next type, real. This type is to represent real numbers. Real number is, you can think of a real number including integer numbers, rational numbers, and irrational numbers. If we have real numbers, why do we need the integer or integer 64 data types? So it turns out that your computer is more efficient when you are doing some arithmetic operations in numbers when they are of type integer, for example. Just that. You can see here the range for this particular type, which goes, well, this E here is a representation of real numbers using scientific notation, and it means that this number 1.1 is multiplied by 10 to the power of minus 38. So this is 0 point and 38 zeros after that. So that's quite a wide range of numbers that you can represent using this real type. For those of you with programming skills, it is worth to mention that the real type in the RealFlow graphs is the equivalent float type in the C and C++ languages. Next type, string. This is quite straightforward. Is just for the representation of text, for instance, RealFlow or sentences or letters, etc. Okay, next slide. Here we have more basic types, but in this case we named them basic extended types, and this extended name here is used because those basic types are extended using the basic types we have seen before. Especially all the types that you have here are using the real data type for the components. So color 4, for instance, this type represents a color using the RGB color model. And we have 4 components because the last component is used for the alpha. Here you can see an example. In this case, RGB 0.5 means a gray constant color. and the range for every single component is from 0 to 1. Next basic extended type is vector3, and this type is for representing points and vectors in the three-dimensional Euclidean space. A RealFlow scene is described in terms of a three-dimensional Euclidean space, so objects have positions, orientations, and those values must be defined using this vector3 type. As I said before, the components of the vector3 are of type real, and you can see here an example. Next type, matrix 4. This type represents a 4x4 matrix. In mathematics, a matrix is basically a rectangular array of data arranged in rows and columns, as you can see here in this example. You know very well that matrices are very useful when you want to transform your points and vectors in the three-dimensional Euclidean space. As I mentioned before, every component of the matrix is of real type. The next type here in this list is quaternion, and this type is especially useful to encode rotations and orientations in the three-dimensional Euclidean space. Why we use quaternions? Basically because they are more numerically stable than matrices, and also because they use less memory space to encode the same transformation. And every component of the quaternion is of real type. And the last basic extended type is box, which is basically rectangular in the three-dimensional space, where its bounding space is defined using the minimum and maximum points of the minimum and maximum corners of the rectangle. Okay, that's all for the basic and basic extended types. I want to talk now about one special type in the RealFlow graphs called polymorphic. To explain why this type is needed, let me present a problem that you have when designing a graph system like the one RealFlow implements. Let me bring a couple of nodes to the scene. I'm going to be creating a custom real, another one. I'm going to create also a custom, in this case, integer, and another one, constant integer. Okay, now imagine that we want to add those real numbers together. You are going to be looking for a node called add real, or maybe add. But now imagine that you want to add those integer numbers together. Probably you will look for a node called add integer. But now imagine that you want to add these real and integer nodes together. Probably you will be looking for a node called add real and integer. And the same for all the other types. Obviously, following this strategy results in a blow up in the number of nodes and also the complexity of the graphs, as you need nodes that do the same for all the available types and their combinations. A crazy thing. To solve this problem in RealFlow graphs, we have introduced the polymorphic type. So that in this case, this particular case, I just can bring an add node to my simulation graph, and I want to show you something interesting here. If I right click on the input pin here, you see the type, which is polymorphic as expected, and here you have all the types that are accepted for this input pin. We have the real one, so this means that we can connect this output pin to this input pin. And you can see that as we drop, the connection is created and the color of the input becomes blue, meaning that this connection has been specialized. If I right click here, you see that now the type is real. Okay, now imagine that I want to add this real number with this integer number. So first, let me show you what types can be used in the other input pin. Is still a polymorphic type, but in this case, the range of types that can be accepted are different. Let me bring an add node again, so I can show you and you can compare the list of available types in one case and the other. Now here you can see that we have quaternion, matrix, etc. But once this input pin here has been specialized, only some specific types are accepted here. In this particular case integer 64 and real. Maybe and the reason why this polymorphic type has been narrowed is because probably it makes sense, obviously, to add a real type and an integer type, but it's not clear if mathematically makes sense to add a real type to a quaternion type, for example. So now I can show you how I can connect this node to the add, so you are adding a real and integer number together. I want to talk now briefly about one important concept within RealFlow graphs: arrays. An array is a list of things. It is a container of things, so to speak. In this case, we have here an array of integers and an array of real numbers. Within a RealFlow graph, for instance, to give you just an example that you can understand, the list of the positions of all the particles that are created or emitted from a specific emitter are stored in an array, where the elements of the array are obviously of type vector3. The most important thing to know about arrays is that everything is an array. Even if one input pin can accept only one element, internally that is an array of size 1. Okay, there is one whole video dedicated to arrays, so I will leave the arrays subject here and encourage you to watch it after this one. Just doing things within the graph using the basic types explained it so far is very boring. In RealFlow, you have particles, you have geometry, you have fields, etc. So to be able to work and manipulate that RealFlow data, you need to extend the basic types, and we call them complex types. Okay, let's start with the first one, which is image, and this type just represents a two-dimensional image. The next one, the mesh type, represents geometry. In RealFlow, mesh is a collection of vertices, edges, and faces that describe a polyhedral object in a three-dimensional Euclidean space. Want to mention that in RealFlow the faces are just triangles. Next one in the list, the object mesh. This type just represents the geometry of an object. And for instance, to get the mesh of a cube primitive or the geometry of a multi-body object, etc. So now you might wonder why we have a type for the mesh of objects and why don't we use the mesh type here before. The reason is just efficiency, but I don't want to get into a detailed explanation of this because the only thing that I want to do is just stress out the idea that this type, object mesh, is going to be deprecated in future versions of RealFlow. And we need it right now just for legacy issues with our internal structured data for the mesh. And when working with the simulation graphs or graphs in RealFlow right now, most of the times you are going to be converting the object mesh to the mesh type, so you can do operations on the mesh, for instance, at the selection or other things. The next one type is the real wave mesh, and this type represents the geometry of real wave. The explanation about why and how to use this type is exactly the same that I give before for the object mesh. Next type, particles, is just a collection of particles or a particle system. Next one, mesh voxelization, is a type for variables that are used for as a celebration structure to speed up geometry search operations. In the future, we are going to be showing some graphs in action, and I will be showing you how to use this voxelization. And the next one is the vector 3 field. This is quite interesting data type, and this type represents a field of data where the basic type of the data in this particular case is vector 3. So what's a field? A field is just a region or subset of the 3D dimensional Euclidean space where we associate one scalar or vector, in this case value, to every single point inside that space. And the next type is real field, which is exactly the same that I said before about the vector 3, but in this particular case the data that we are storing in the field is of type real. Distant field. This type represents a signed distant field, or SDF. There are a lot of documentation about what an SDF is on internet. Is a very easy concept to understand, and here I'm just going to explain what is basically. And is a field of real type where the value at a specific point is the smallest distance from that point to an arbitrary surface. And that surface can be defined by a geometry, a mesh, or it can be also defined with particles. The next type, curve. This type represents a spline curve inside RealFlow. You know that spline curve is, in mathematical terms, is a polynomial function that is smooth and that is piecewise defined. You know very well that any 3D application nowadays have one way or another of dealing with these curves, and they can be used to define the path of an object or how a specific parameter is changing over time, etc. And the last one, the last complex type, is the key, which is just basically a control point of the spline curve. The power on simulation graphs is the ability to change, manipulate, and edit the things that are happening in your RealFlow scenes. So to be able to do this, you have to bring the RealFlow scene nodes to the graphs world. So to have the types of those elements in your scenes, in your graphs, those types cannot be the basic types and cannot be the complex types either. You need one special new types which we call scene node types. And you can find here, you can see the list of the RealFlow nodes, standard emitters, for instance, the circle, the square, and the scene node type, standard emitter in this particular case. So you can see that we have one scene node type for every single RealFlow scene node. So this is the full list of nodes, of types, sorry, but I want to draw your attention in this particular one, RealFlow node. This scene node type is especially created to deal with arrays, and I think that the best way to explain this scene node type is by using an example. So let me go to RealFlow. So I'm going to clean the scene. Okay, and now I'm going to add some RealFlow nodes to this scene. For instance, I'm going to add a couple of standard emitters and habit domain. I'm going to add a couple of daemons as well. Okay, let me change the layout a little bit so you can see better what I'm going to do. And I can even minimize this singly because I don't need it. Okay, so I'm going to explain you what I'm gonna do. I'm gonna get the full list of nodes, RealFlow nodes, into the graph right here, and I'm going to change the name of all the nodes. I'm going just to put some prefix in the node. So we have one special graph node to bring all the nodes to the graph call, which is get nodes, get all RealFlow nodes. Okay. So now I'm going to bring a node that get the name of the node. I'm going to connect both. And now just let me bring a string node where I'm going to type the prefix. In this case, doesn't matter. For instance, prefix. So I'm going to need a node that will compose the prefix with the name of the node. For such thing, we need string concat2, I believe. Yes, okay. So this is, sorry, I was doing the other way around. So the left is going to be the prefix and the right is going to be the node name. We can even write a separator here, for instance, underscore. Okay. Okay, so I am going to need a node to set the new name to the node, which is set node name. And this is the name, and here we have the array of nodes. And finally, I'm going to create an evaluator node. So if I run this graph, the name of the nodes is going to be changed. Okay, here we go. So there is one special node that is very handy when you are dealing with an array of RealFlow scene nodes, which is, I believe, node dmax. Okay, so what this node is for? This node allows you to filter the array of nodes depending on the scene node type. For instance, imagine that we want to process all the emitters here and we are going to change their name again. But in this particular case, we are only interested on the emitters. So this output here is the list of emitters, the array of emitters. So if I move this part of the graph here, I'm going to be able to connect the array of emitters to the two different inputs. Okay, to see the difference, I'm going to change the prefix. Instead of prefix, I'm going to be writing, for instance, emitter. Okay, so if I run this graph again, you see now how I am only affecting the emitters here. Okay, that's it.